Okay, in this video, we're going to be talking about a new data type, the stack abstract data type. So a stack is something you're actually already familiar with. We've seen it in terms of the runtime stack that we use to hold activation records, but now we kind of elevate that idea of stack to be a true data type that we can use for any purpose within our program. And so in that context, a stack is an abstract data type of ordered items that are only inserted on or removed from the front of a list. So for example, one of the operations I'm going to do on a stack would be a push. And whenever I push, I always push to the front. So I'm representing the front here by, this label. So the top of these boxes is the front of my stack. And so I can push A. When I push A, it goes to the front. And then when I push B, B is now at the front and A comes after it. When I push Z, Z is now at the front and B and A follow it, and so on. And then when I pop, I remove from the front. I don't go to the end to remove. So in this case, if I just push Z and then I do a pop, I'm going to pop Z, and that leaves B and A. And then when I do another pop, it pops B, leaving just A, right? So I only insert at the front and remove at the front, or we're going to call it push and pop in the context of a stack. And there are some common operations you could then imagine we can implement on a stack abstract data type. Push and pop are the ones I just described, right? So if I have some stack object and I want to push X, then I would describe that as a push onto some stack, the value X. Likewise, if I want to remove an item, I can say pop stack. Now, typically when we talk about popping, we're not actually getting the value that's on the stack, we're just removing it from the stack. So if we actually want to get the value that's on the front of the stack, then we call that peek. And that returns the value from the front of the stack. You could do pop and peek together, but just to be really clear about what we mean, we're separating out these two ideas. Empty will tell us if the stack has anything in it. And then size is just another way of querying some information about the stack, and it tells us the number of items in the stack. So these are very common things you might want to know or might want to calculate about a stack abstract data type. Now, what's a stack good for? Well, it's good for quite a number of things, but maybe one of the simplest things you can immediately see about a stack is that it's good at reversing things. Whatever order you stick them in, you get them out in the opposite order. So what we could do with that is say reverse a string of characters. So what if I'm getting some characters out of a string? Then what I could do is as I get each character out of the string, and this is just kind of pseudocode I'm showing over here. This isn't actually C code or C++ code. So as I get each character out of a string, I push it onto a stack. And then after I've gotten them all, while the stack is not empty, I look at what's on the top of the stack and I print it out, and then I'll pop it. Okay, and so what that would do is it would stick everything in the stack and then remove them one at a time, printing them as you remove them. And that's going to have the effect of reversing the string. We can see it over here pictorially, right? So if my string is A, B, C, D, then first I'll push A, then I'll push B, then I'll push C, then I'll push D. And when I get done, then the order of my stack is actually D, C, B, A. So as I pop them, I'm going to first pop D, then I'm going to pop C, then I'm going to pop B, then I'm going to pop A. And so what I'll actually do is print them out D, C, B, A as I pop them in the reverse order. So a stack is really convenient for reversing things, but that may just seem like a little gimmick. But are there other situations where we really do need to remember things in reverse? Well, there are, right? We know that on the runtime stack, when we're calling functions and a function's done running, we don't jump back to the very first function, main. We jump back to just the previous function that was executing, right? And we return to them in the opposite order that they were called in, right? So the runtime stack, we know, provides this characteristic of doing things in reverse that we need. Another example of doing things in reverse might be if you're looking for a path through a graph and then you want to return the same path that you took. Well, that would be a stack, right? So you go through some sort of sequence of steps, and then you want to return the same way. And that might be really helpful if, say, you want to give somebody directions in the opposite order that they, followed a map. So stacks just tend to show up when we're doing a lot of things. They're just really handy, and they're convenient conceptually in a lot of situations. It's actually pretty easy to implement a stack using a list. Push is the same thing as inserting at the head of a list, and pop is the same thing as removing at the head of a list, both of which are operations we've implemented for our lists. So we have support for both of these, which means if we have a list, we can implement a stack really easily. So let's take a look at how we might do that. So here's a stack class, and what I'm going to do is put a list object inside of it, and I'll make it private. And that way, no one can grab that list and perform an operation that doesn't conform to the stack, right? Inserting something in the middle, for example. So we make list private so nobody can use it in a way we don't want. And then we provide prototypes for these 4 key functions that we know we need on a stack. We need to be able to push an item, we need to be able to pop an item, we need to be able to grab the top with peek, and then we also might want to check if the stack is empty. And since our list deals with items, then our stack is going to deal with items as well, whatever those items happen to be. Okay, so for our push, the implementation of push, and I'm assuming that stack class I just showed you is in some header file, stack.h, and then we implement these functions in a C++ file, and we'll call it stack.cpp. Then what I'm going to do in push is I'm going to take that item and insert it at the front of my list. And so when I want to insert something at the front of my list, I can use the insert after, and I pass in a null iterator. And so if I just declare an iterator this way, then by default, the default constructor will initialize its internal node pointer to null. So just declaring an iterator gives me a null pointer. And then when I call insert after this with a null iterator, that means I'm going to insert at the head. And then I just pass in the item I want to insert. So this call list.insert after will take care of inserting this item at the front of my stack. Okay, and then when I want to pop, I'm going to use remove after. And again, the same logic applies. If I give remove after a null iterator, then it removes the front of the stack. So I just call remove after with a null iterator, and that pops the front of the stack. So that's pretty simple. I didn't have to write much code. I just use my list object that I already made, and now I'm up and running with a push and pop. Now, how about peek and empty? Well, for peek, what I need to do is get the item at the beginning of the list, at the front of the list. That would be what's at the top of my stack. And so I can use an iterator and get an iterator that points to the beginning of the list. Since stack doesn't have permission to just look inside the list, it can't just grab the head pointer and grab the information out of it. It can't do that. It's got to use an iterator to get an object, a handle to the first node of the list. And then with that iterator has a function called getItem that gives us a reference to the first item. And then we return that from peek. Okay, and then empty is pretty simple. List has its own empty function, right? It's one of the first things we implemented. If head is null, we know it's empty. And so we just call that list empty and return the result. And that tells us the stack is empty. Okay, and with that, we're done. We've implemented a stack data type. And so now we can use it maybe to read in strings and reverse them. But in this situation, I'm not reading in the individual characters of a string and reversing them like I showed you before. What I'm doing is reading in a bunch of strings, reading in strings in one order, and then printing them out in the reverse order. So what I do is I include my stack.h here in another source code file. And then I declare my stack object in main. And then while true, I'm just going to use cin to read in a bunch of strings. And as long as that string is not equal to quit, I push it into my stack. And so this will just build up a stack with a bunch of strings. And then after I read in those strings, I have another loop that says while my stack is not empty, then get the top of the stack, stack.peep, peek, and print it out, and then pop it. Okay, so this will print out each thing that's in the stack one at a time and then remove them so that eventually I see everything that was in the stack. And this is going to print them out all in reverse order. The way you would compile this code that I've implemented, you can just do it all in one step with G++. You just say the name of the program you want to create, main in this case, and then the code I just showed you that does that reversing of the strings, I put that in a C++ file called main. The stack code is in stack.cpp. The list code is in list.cpp. You just list all these source code files out together. Have a couple of extra flags here to just make sure the compiler works the way we want. And then this is going to create a program called main that you can run. And you can get all this code in my GitHub repository. You can download it and run it yourself. Okay, so what's the time complexity of our linked list-based stack implementation? Well, it's pretty good. When we push, we're using our list and we're pushing one element to the front of a list, which we know is O1. So that means our stack also has O1. When we pop, we're removing an item from the head of a list, which we know is O1. And so that means our stack implementation is O1. When we do the peek, we're just getting the head of the list, which we can also do in O1. So that means peek is O1. Empty, we're just checking if head is null. So that's a fast operation. So that's also O1. We didn't implement size, but you can also do size in O1. If every time you push, you increment a counter, and every time you pop, you decrement a counter, then you can know how many things are in your stack very easily. And so that would also be O1. Okay, so in summary, stacks order data in a last in, first out manner and support push and pop operations. Stack can have an efficient implementation in terms of a linked list. Since we've already implemented a list, we can just use it to implement our stack. It's also worth pointing out that stacks can also be implemented efficiently using an array. Now, hopefully you already know that and realize that because that's what the runtime stack is. It's just a stack implemented as an array. And so lists aren't the only way to do it, but they are a convenient way to do it because we don't have to worry about the size of that array ever being exceeded when we're adding and removing things from the stack.